the system. So we will now look at the second case, case 2, where you have, remember that we had R and W as inputs. We will have R equals 0, but W of S is not 0, which means that we want, there is disturbance on the system, and we want disturbance rejection from our system. So the two things that control system must do is good tracking, which is follow R, and secondly, reject the disturbance, that is, the disturbance should be eliminated. So error is R minus Y of S. R is 0 here, we assume. There is no change in R. So it is minus Y of S, as a matter of fact. And this is simply minus G of S divided by 1 plus G of S, C of S, W of S. W is the disturbance. And we might call this thing, this whole thing, TW of S. Okay. Disturbance transfer function, let's say. Okay. So remember that we had the following picture. Let's try this. Now this R of S here is 0. We don't want this. Well, we don't have this. We don't change this thing. So this is W of S. This is the error. This is G of S. This is Y of S. And there is feedback. So this thing is non-existent. We can think about as there is a single input for this system. Now we can also, just as we have defined the system type for a reference input R, we can define the system type for disturbance, let's say, W of S, as follows. If you have a type 0 system, the step disturbance results in finite steady state error. Okay. So there is a step disturbance, but the response cannot go to 0. It stays at a finite value. Type 1 system, in which the ramp disturbance results in a finite steady state error. And for a type 2 system, parabolic, let's say, disturbance results in finite steady state error. So, for example, for a type 1 system, for a step disturbance, the steady state error will usually be 0. So this is more or less how we define it. Here we can write TW, the disturbance transfer function, can be written as S to the n times, let's say, TW0 of S. Now these are the free differentiators, if you like. So the steady state error is equal to, again, by final value theorem, S times TW of S, by our definition. So limit S goes to 0 of S times TW of S is just a second, I just missed something here. Times W of S. Okay. And this is equal to, again, limit S goes to 0 of S times TW. Instead of TW, I'll just put this one here. Now, W of S is depending on whatever polynomial you have 1 over S to the K plus 1, as you might remember. Okay. So this S and this 1 cancels, and what you have is limit S goes to 0 of S to the N divided by S to the K times T W0. We want this ESS to be 0, as you might remember. So the cases are if N is greater than K. Okay. This again corresponds to, as you will see, the number of free integrators more or less, but we will see there is a difference here. If N is greater than K, the steady state error is 0. If N is equal to K, the steady state error will be TW of 0, which is finite. And this gives us the system type for the disturbance. If N is less than K, the steady state error would be infinite. Okay. This part is important because this gives us the system type for disturbance. Gives us the So the system type is defined for both for reference input and for disturbance, okay? And they might be different. They don't have to be the same. They might be different things, okay? Let me give you an example. That would be the best understood through an example, I suppose.
Hocam, can I ask a question?
Yes.
Hocam, we want a system that has error is equal to 0, right?
Yes.
So in this case, the best choice is the system that has bigger N than K, right, hocam?
Yes, that's true.
Okay, that's all I want to ask. Thank you so much.
Oh, you want the following. Let's say that there is a disturbance on the system. This is y of t. If your system, if there is a disturbance on the system, your response should look like this. Disturbance will cause a disturbance on the system, but eventually you should settle at 0 because this is what R is. Okay, this is a good response. But if you have a response like this one, here you will be having the disturbance causes a steady state error. Okay, and this is not good.
Hocam, in the real life, is it possible to have a zero error in the system?
Sure, sure. Of course. As we said, you want the arm to rotate 90 degrees, it rotates 90 degrees.
I see.
Actually, it is almost always the case that you have zero error. Well, unless you design it improperly.
Okay, hocam, thank you so much.
Yeah.
Hocam, sorry to disrupt you, but I think I don't get how we use type 0, type 1, and type 2, and how we define in a system if it's going to be type 1 or type 2 or type 0 in our question.
Yes, as I said, I have introduced too many concepts in the same time, and it's a little bit difficult to understand at this point. Basically, type 0 systems have steady state error of, if you have a step input, okay, and also it also depends whether you have a disturbance or a reference input. If you have let's say that you have a reference input, okay?
Okay, hocam.
Let's say that we have R is not 0, W is 0, okay? If you have a type 0 system, you have a step input R of let's say steady state. Your type 0 system has some steady state error to let's say to a step input. This is ESS, okay, type 0. Whereas if you have let's say R equals 0, but W is not 0. For this case, there is a disturbance on the system. And your system is going to respond like this. The disturbance will cause some steady state error from here. Okay. Because in this case, R is 0, you want your response to go to 0 eventually, or whatever value you choose, but it doesn't go to 0 anymore. It just stays at a certain value. Okay. The control system should reject the disturbance, but it cannot. So type 0 systems are, it is possible, but it is better to have a type 1 system. In the type 1 system, let's say R is not 0, W is 0. So you look at tracking. If you have a step input is step RSS, the response will look like this. Okay, so the steady state error will be 0 for a step input. But if you have a ramp input for a type 1 system, this is the R of C equals some C, let's say. In this case, there will be some steady state error. Oh, sorry, say another color. You see, eventually you have a steady state error. And this is defined by 1 over the velocity coefficient, 1 over kV. Now, type 1 systems are, as I have said, they are the most common things that are used. Usually, type 1 systems have single integrators in them. And that is the principle of integral control. If you use integral control, you usually have a type 1 system. On the other hand, if you have a type 1 system with R equals 0, but W is not 0, what you have is there is a disturbance on your system, but your system gets disturbed, but eventually it reaches 0. Okay? If this is a step disturbance, the steady state error gets to be 0. Okay? Well, you'll get to understand this better as I get more examples, I hope.
Hocam, correct me if I'm wrong. So we are just first need to draw the graph, then we choose if it's going to be type 1 or type 0. We can see from the graph what is going on in the system. Then we see
No, it is
type
not.
0.
You just look at the transfer functions. You don't look at the responses. If just from looking at the transfer functions, you can determine the system type. Okay? It is not that difficult. Actually, as I have told you, for the case, most of the cases we are examining, it is just the number of free integrators in the system defines the system type. Okay? If you have a system like, you know, G of S equals, let's say, 1 over S plus 2, C of S, the controller is S plus 5 over S, let's say. L of S is simply GC, which is
S plus 5 over S squared plus 2S.
S times S plus 2, right? Here you have one free integrator. For this system, if you have unity feedback, it's simply type 1. At least for R, let's say, okay, for R input. You cannot say that this is type 1 for W input. It is not very easy to say that. It just depends. It depends on whether you have, well, we will see. I will try to show this. Actually, I think this is type 0 for W input. But I will show this by an example. Or it might be type 1 also. We will see. Let me give you an example here. Let's say that G of S, the planned transfer function is again 1 over S times S plus 1. C of S is a PI controller, K1 plus K2 S over S. Okay. So we want to determine the system type for R and W. Okay, this is the, you have two free integrators, n equals 2, two free integrators, as you see. And actually, we can, L of S can be written as 1 over S squared times K1 plus K2S over S plus 1. And we can call this L0 of S if you like. Okay. The steady state error would be, from our definition, limit S goes to 0 of S to the K. Now, if K is equal to 2, this thing that cancels this S squared, and you will have finite steady state error. For K equals 2, okay, the steady state error would be, well, the limit S goes to 0 of 1 over S squared plus L0 is this K1 plus K2S over S plus 1, okay, which will be K1, no, 1 over K1. Yeah, 1 over K1. Okay. Which is finite. So this K equals 2 gives you the system type. So let's say for K equals 2, the steady state error is 1 over K1. So system type equals 2 for R. Okay. We were looking at R. For B case, for W, well, we will see that TW of S, which is
Oh,
minus,
hocam,
yes,
I'm again sorry to interrupt, but
yes,
so we said K equals 2 means polynomial. So this means the type 2 is like in the table type 2 work for parabola, as I remember.
mhm.
So that's why we say it's going
Uh,
to be type 2.
yes,
And so how, like, actually, why do we set for just R?
well, we study them just in one by one, that's why. Because they are, the system types can be different for R and W, that's why, as we will see here.
Hmm.
Okay?
Hocam, isn't it should be minus in the
There's a minus.
okay.
Yeah. So this is TW of S. Okay. Now the steady state error is the limit s goes to 0 of tw of s times 1 over s to the k, which is limit s goes to 0 of s divided by s plus s plus k times 1 over s to the k again. And you see that this s cancel, if this s be cancelled, this s, k should be equal to 1. If k is equal to 1, ESS would be minus 1 over k1, which is finite. Okay. So as we see here, the system type equals 1 for W. So they are different. The system type for R and W are different. Okay. Okay. Do you have any questions? This is, this topic is actually, it's quite easy, but the way it is presented with all these concepts thrown in the same time, it is, it is, at first, it's hard to understand. But on the other hand, there is nothing too difficult about it. It's just too many things are put together at the same time. So it's a bit confusing in the beginning, but it's not that hard. Basically, you have to remember that the system type is determined for most of the cases by the number of free integrators. The integrators in the system improve the steady state performance. But as we will see, they tend to destabilize a system. Okay. So stability and steady state error requirements are usually contradictory. So we have to be careful about that. Okay, I have an example, but that example I don't think we will be able to finish now. I don't think we can do it in the 20 minutes we have left. So let me try to do something else. Okay, at least let me give you this example. One more example. probably. I will just study this example more in detail the next time, possibly with using MATLAB and so on. This is the thing we look at many times in this course. Let's say that there is an arm which you want to rotate, right? With a motor connected to it. Okay. So you apply a voltage, and that creates a torque, and that torque rotates the arm an angle of theta. Okay. So the equation of motion for this arm is, as you might remember, the torque is the polar moment of inertia times the theta double. This is the equation of motion, and the transfer function, which is theta of s, the output, divided by the torque, is 1 over js squared. Okay. Let's say that the torque is proportional to the voltage, so that you can just consider it as a constant. For example, let's say that you have a motor. Let's say this is the arm. The motor, the torque is generated by the motor, let's say V of S. V is the voltage applied. Let's assume that this is K motor divided by the time constant of the motor, S plus 1. Usually the motors are fast, so that we can ignore the time constant. This thing is small. You can assume that this is Km. So we assume that the motor time constant is 0. Okay? So that the theta of S versus the voltage angle, we can say that this is theta of S times T of S, which is the arm, and the motor transfer function T of S over V of S is the motor transfer function, which is Km approximately, divided by Js squared. Okay. Okay, so we can control this with a let's say so our system looks like this. This is the arm, 1 over Js squared. Torque comes in, theta goes out, theta of S. And the torque is generated by the motor, which we will assume it to be Km. So the voltage comes in, and the voltage is generated by the controller, whatever the controller is. Well, let's not. Controller is C of S. And the controller is driven by the error, and the error is R of S, which is, by the way, I will just say that. Negative feedback. This is the R of S is the reference value of theta. Okay. So what this system does is, as I have told you, you want this system to rotate some degrees, let's say 90 degrees, open the door or something like that, and then the door gets opened. Okay. You give a certain command, and the control system somehow achieves that command by giving the necessary rotation. Okay, so this is one thing. Here we are looking at the problem of command following. Okay. It might be possible that in this arm there might be some, well, I don't know how, but there might be some disturbances, like a disturbance torque. As you try to rotate it, there might be an adverse effect due to, I don't know, some extra weight or some wind or something. In
Hocam,
this
can I ask a
case,
question?
yes.
Hocam, in the torque constant, you assume that it is zero because like the velocity of the torque is so high, it cannot affect the system of the torque. Why we assume that Tm is equal to zero, hocam?
We assume, you mean this one?
Yes, hocam.
The time constant. Well, usually what happens is that the motors of systems, motors are usually quite fast, okay? Especially compared with the dynamics of an arm, which is a robot arm. The motors are much, much faster, okay? So their time constants, they might be in the range of milliseconds or just, some, let's say milliseconds, let's say 100 milliseconds or something. But the arm rotates in seconds, okay? So there is a degree of speed between them. Let's say if the motor is 10 times, 100 times faster than the arm, then you can compare with the dynamics of the arm, you can neglect the dynamics of the motor because the dominant response would be the arm dynamics. Okay.
Thank you,
That's
hocam.
all.
Thank you so much.
Okay. Now, if there is a disturbance on this system, we just modify it as follows. There is this, again, Km, but there is a W of S, which is the disturbance torque. 1 over Js squared of S. That is the control, C of S. There might still be R of S. Here, the aim is disturbance rejection. We want to eliminate the, let's say, effect of okay. Okay, so let's say that for the steady state error, and this is how I will stop after doing this. Let's say that our G of S is Km over Js squared. And C of S is just simply a K. Let's still call it Kp. Okay, Kp is the proportional controller. This is the controller, which is proportional. So L of S is Cg, which is Kp over Js squared. And as you see, it has two free integrators. For R of S, the steady state, we want to find the system type. The system type is simply, as you might remember, the steady state error is limit s goes to 0 of well, you have to have s squared here, okay? Um, for k equals 2, the steady state error will be j over kpkm, I suppose, which is finite. So, system type is 2 for R of S, okay? Which you can expect because there are two free integrators. For the disturbance for W of S, okay, you find the disturbance transfer function, which is minus 1 over G over 1 plus GC, which is Km over Js squared divided by minus 1 plus Km over squared. What do we get? Js squares get cancelled. Well, only you can add 1 over s here. These s's cancel. This one and that one cancels. So what we have is ESS equals minus 1 over KP for unit step disturbance. So if you have a steady state error for unit step disturbance, then the type is system type equals 0 for, and it's interesting because for this system you have for command following you have system type is true. For disturbance rejection, system type is 0. Okay. So you cannot really reject any disturbances here. Well, you cannot reject step disturbances, even step disturbances. Well, so you have to do something here. But we are out of our time, so let's stop at this point. We will continue the next time.